Download this code from codegive.com, link in the description below. Acid properties and race conditions, a deep dive with code examples. This tutorial dives deep into the concepts of acid properties and race conditions, explaining their significance in database management and concurrent programming, respectively. We'll explore each acid property in detail, then move on to race conditions, their causes, detection, prevention, and finally, the relationship between acid and race conditions. Code examples in Python and potentially SQL will illustrate the concepts. Part 1, Acid Properties in Database Transactions. ACID is an acronym that stands for atomicity, consistency, isolation, and durability. These four properties are crucial for ensuring the reliability and integrity of data in a database system, particularly when multiple transactions are occurring concurrently. 1. Atomicity ****. Definition ***Atomicity ensures that a transaction is treated as a single, indivisible unit of work. Either all operations within the transaction succeed, or none of them do. It's an all-or-nothing guarantee. If any part of the transaction fails, the entire transaction is rolled back to its initial state, as if it never happened. Why it's important Imagine transferring funds between two bank accounts. You need to deduct the amount from one account and add it to the other. If the deduction succeeds, but the addition fails, example due to a network error, you would have money disappearing into thin air. Atomicity prevents this data corruption by ensuring that both operations happen or neither does. Implementation Databases typically use transaction logs to track changes. If a transaction fails, the log is used to undo any partial changes. Code example, Python using SQLite and SQLite 3. Explanation The transfer_funds function takes the database path, from account, to account, and amount as input. It establishes a connection to the SQLite database. Con.execute, begin transaction, starts a transaction. It performs the deduction and addition operations using update statements. Cursor.rowCount is used to check if the update queries affected any rows. If not, meaning the account doesn't exist, a value error is raised. Con.commit, commits the transaction, making the changes permanent. If any exception occurs during the transaction, con.rollback, rolls back the changes, ensuring atomicity. The setup_db function creates the accounts table and populates it with sample data. It also clears any existing data for testing consistency. The example demonstrates both a successful transfer and a failed transfer, due to a non-existent account. The final select statement prints the account balances, allowing you to verify the effects of the transactions. 2. Consistency Definition Consistency ensures that a transaction brings the database from one valid state to another. It enforces predefined rules, constraints, and integrity checks to maintain data correctness. A transaction cannot violate database constraints. Why it's important Consider a database schema with a constraint that all account balances must be non-negative. If a transaction attempts to withdraw an amount that would result in a negative balance, the transaction should be rolled back to prevent the database from entering an invalid state. Implementation Consistency is achieved through database constraints, example not null, unique, check, triggers, and stored procedures. These mechanisms enforce rules about what data is allowed and how it can be modified. Code example, SQL, assuming MySQL or PostgreSQL, adapted to SQLite in the Python example. Asterisk explanation asterisk. Asterisk the create table statement includes a check, balance equals 0, constraint. This ensures that the balance column always contains a non-negative value. Asterisk the insert statement attempting to insert a negative balance will be rejected by the database due to the constraint. Asterisk the update statement within a transaction might succeed initially, but the commit statement will trigger the constraint check. If the update results in a negative balance, the transaction will be rolled back, preserving the database's consistency. Asterisk extending the Python example to include a check constraint, SQLite adaptation. Asterisk important notes on SQLite and consistency. Asterisk SQLite doesn't enforce check constraints as strictly as other databases, like MySQL or PostgreSQL. It may allow the insertion of invalid data in some cases. The Python code manually checks for the negative balance before committing the transaction. This is a common approach when working with SQLite or when more complex consistency rules are needed. In a real-world, production system, you might prefer a database system with more robust constraint enforcement. 3. Isolation asterisk asterisk. Asterisk definition asterisk isolation ensures that concurrent transactions operate independently of each other. Each transaction should appear to be executed as if it were the only transaction running on the system. This prevents interference between transactions, ensuring data integrity. Asterisk why it's important asterisk imagine two transactions simultaneously trying to update the same bank account balance. Without isolation, one transaction might read the balance before the other transaction updates it, leading to lost updates or other inconsistencies. Asterisk implementation asterisk databases use various locking mechanisms and concurrency control protocols to achieve isolation. Common isolation levels include asterisk read uncommitted asterisk the lowest level of isolation. Transactions can read uncommitted changes made by other transactions. This can lead to dirty reads. Asterisk read committed asterisk transactions can only read committed changes. Prevents dirty reads but can still lead to non-repeatable reads. Asterisk repeatable read asterisk transactions can read the same data multiple times within the same transaction and get the same results. Prevents dirty reads and non-repeatable reads but can still lead to phantom reads. Asterisk serializable asterisk the highest level of isolation. Transactions are executed as if they were executed serially, one after another, preventing all concurrency anomalies, dirty reads, non-repeatable reads, phantom reads. The choice of isolation level involves a trade-off between data consistency and performance. Higher isolation levels offer better consistency but can reduce concurrency. Asterisk code example, illustrative, using threads to simulate concurrent transactions in Python. Asterisk explanation asterisk. Asterisk the code uses threading to simulate two concurrent transactions. Asterisk the transfer_funds function includes time.sleep, calls to simulate some work being done within the transaction, increasing the chance of concurrency issues if isolation is not properly enforced. Asterisk the SQLite database, by default, uses serializable isolation level if not overridden by the user. This would prevent concurrency issues. If another isolation level were set in a different database, race conditions could occur. Asterisk demonstrating potential isolation issues, if the database is improperly configured or if lower isolation levels are used. One lost update asterisk if two transactions read the same balance and then update it based on their respective reads, the update from one transaction might be overwritten by the other. Two dirty read asterisk if one transaction updates the balance but doesn't commit, another transaction might read the uncommitted, dirty, data. If the first transaction rolls back, the second transaction will have read incorrect data. 3. Non-repeatable read asterisk a transaction reads a balance, and then another transaction updates that balance and commits. If the first transaction reads the balance again, it will get a different value. 4. Phantom read asterisk a transaction executes a query that returns a set of rows. Another transaction inserts new rows that would have been included in the original query. If the first transaction re-executes the query, it will see these phantom rows. Asterisk important note asterisk to realistically demonstrate isolation issues, you would typically need a database server with more configurable isolation levels than SQLite's default. You'd also need to carefully craft scenarios where transactions access and modify the same data concurrently. The example above primarily illustrates the concept of concurrent transactions and the potential for problems if isolation is not enforced. 4. Durability asterisk asterisk. Asterisk definition asterisk durability ensures that once a transaction is committed, its changes are permanent and will survive even system failures, example power outage, disk crash. Asterisk why it's important asterisk if a bank transaction commits successfully and then the database server crashes before the changes are written to permanent storage, the transaction could be lost. Durability prevents this data loss. Asterisk implementation asterisk databases typically use write-ahead logging, WAL, backups, and data replication to achieve durability. Asterisk write-ahead logging, WAL changes are first written to a transaction log before being applied to the database files. The log is written to persistent storage, disk. In case of a crash, the log can be used to replay committed transactions and undo incomplete transactions. Asterisk backups asterisk regular backups provide a point-in-time snapshot of the database, allowing recovery from data loss. Asterisk data replication asterisk data is replicated to multiple servers, so if one server fails, another server can take over. Asterisk code example, conceptual, showing the importance of database configuration. Asterisk explanation asterisk durability is largely a matter of database configuration and infrastructure. The code example illustrates the kinds of settings you would need to configure in a real-world database system to ensure that your data is protected against failures. Part 2, Race conditions in concurrent programming. A race condition is a type of bug that occurs when the behavior of a program depends on the unpredictable order in which multiple threads, or processes, access shared resources. It arises when multiple threads try to read or write the same memory location simultaneously, and the final outcome depends on the timing of their execution. 1. Understanding race conditions asterisk asterisk. Asterisk critical section asterisk a critical section is a piece of code that accesses shared resources. Race conditions occur when multiple threads enter a critical section at the same time. Asterisk shared resources can be anything that multiple threads can access, such as asterisk global variables, asterisk files, asterisk network connections, asterisk database connections, asterisk data corruption asterisk race conditions can lead to data corruption, unpredictable behavior, and difficult to debug errors. 2. Common race condition scenarios asterisk asterisk. Asterisk update a counter asterisk multiple threads increment a shared counter variable. If not properly synchronized, updates can be lost. Asterisk check then act asterisk a thread checks a condition and then performs an action based on that condition. Another thread might change the condition between the check and the action, leading to unexpected behavior. Asterisk lazy initialization asterisk multiple threads try to initialize a shared resource if it hasn't been initialized yet. 3. Code examples of race conditions, Python using threading. Asterisk example 1, updating a counter, without synchronization. Asterisk explanation asterisk. Asterisk shared underscore counter is a global variable accessed by multiple threads. Asterisk increment underscore counter function increments the shared underscore counter variable number underscore increments times. Asterisk two threads are created and started, both running the increment underscore counter function. Asterisk the expected counter value is number underscore increments asterisk number underscore threads, 200,000 in this case. Asterisk however, the actual counter value will often be less than the expected value because the increment operation, shared underscore counter plus equals 1, is not atomic. It involves multiple steps: read the value, add 1, and write the new value. If two threads read the same value before either of them writes the updated value, one of the updates will be lost. Asterisk example 2, check then act, without synchronization. Asterisk explanation asterisk. Asterisk shared underscore list is a global list accessed by multiple threads. Asterisk the add underscore to underscore list function checks if the list is empty. If it is, it adds the string first element to the list. Asterisk two threads are created and started, both running the add underscore to underscore list function. Asterisk if both threads enter the if not shared underscore list condition before either of them adds an element, both threads will add the element to the list. 4. Preventing race conditions asterisk asterisk. Asterisk synchronization mechanisms asterisk use synchronization primitives to protect access to shared resources. Asterisk locks, mutexes a lock allows only one thread to access a critical section at a time. Asterisk semaphores control access to a limited number of resources. Asterisk condition variables allow threads to wait for a specific condition to become true. Asterisk atomic operations are operations that are guaranteed to be executed indivisibly. Some programming languages and hardware provide atomic operations for incrementing counters or updating simple data structures. Asterisk avoid sharing data asterisk if possible, design your program to minimize sharing data between threads. Asterisk immutable data asterisk use immutable data structures, which cannot be modified after creation. Asterisk thread local storage asterisk each thread has its own copy of the data, eliminating the need for synchronization. 5. Code examples with synchronization, Python using threading and lock. Asterisk example 1, updating a counter, with lock. Asterisk explanation asterisk. Asterisk threading.lock, creates a lock object. Asterisk with lock acquires the lock before entering the critical section. The with statement ensures that the lock is automatically released when the block of code is finished, even if an exception occurs. Asterisk only one thread can hold the lock at a time, preventing race conditions. Asterisk example 2, check then act, with lock. Asterisk explanation asterisk the lock prevents both threads from entering the if condition simultaneously, ensuring that only one thread adds the element to the list. 6. Detecting race conditions asterisk asterisk. Asterisk code reviews asterisk carefully review code for potential race conditions. Asterisk static analysis tools asterisk tools that analyze code for potential concurrency issues. Asterisk dynamic analysis tools asterisk tools that monitor program execution for race conditions. Asterisk testing asterisk write concurrent tests to try to expose race conditions. This can be challenging, as race conditions are often timing dependent and may not always be reproducible. Asterisk thread sanitizer, tsana dynamic analysis tool that can detect race conditions and other concurrency bugs, available in compilers like GCC and Clang. Part 3, Relationship between acid properties and race conditions. Asterisk acid aims to prevent data corruption in a database environment race conditions, in general concurrent programming, can lead to similar data corruption problems. Asterisk isolation in ACID directly addresses concurrency issues in database transactions, including race conditions. It ensures that concurrent transactions do not interfere with each other. The higher the isolation level, the more robust the protection against race conditions and related anomalies. Asterisk the other ACID properties, atomicity, consistency, durability, also contribute to data integrity, but isolation is the most directly related to race conditions. Asterisk the concepts of locking and synchronization used to prevent race conditions in concurrent programming are similar to the locking mechanisms used by databases to ensure isolation. Example, illustrating the link. Consider the bank account transfer scenario again. If you implemented the transfer logic in a multi-threaded application without using a database with ACID properties, you would need to use locks or other synchronization mechanisms to prevent race conditions. If two threads tried to transfer funds from the same account simultaneously, you could end up with the lost update problem mentioned earlier, which is a type of race condition. By using a database with ACID properties, specifically isolation, the database system itself handles the locking and synchronization, so you don't have to implement it in your application code. The database guarantees that concurrent transfers will be executed in a way that preserves data integrity. Conclusion asterisk. ACID properties and race conditions are fundamental concepts in database management and concurrent programming, respectively. ACID properties, particularly isolation, are essential for protecting data integrity in database systems. Preventing race conditions is crucial for building reliable concurrent applications. Understanding the relationship between these concepts helps you design and implement robust and correct software systems. By applying appropriate synchronization mechanisms, in general concurrent programming, and relying on the ACID properties of databases, you can mitigate the risks associated with concurrent access to shared resources and ensure the integrity of your data.